We are continuing in our unit on electrons and periodicity, and today we're going to talk about characteristics of elements. The topics we're going to cover are going to be the periodic table, periods, groups, and families in the periodic table, metals, nonmetals, and metalloids, and we'll talk about atomic radius and ionization energy and the trends that those show across the periodic table. So, first topic here is going to be on the periodic table. The periodic table was developed by a Russian scientist by the name of Dmitry Mendeleev. Basically, he was interested in the properties of elements, and he had noticed that several of the properties of elements started repeating as you sort of went up along with respect to atomic mass. That if you basically rank the elements in terms of atomic mass, that their properties started repeating as you'd go 8 elements, and then you get something that was similar to the element that was 8 elements ago, and then 8 more elements, you get another element that's similar to the elements that was the element that was 8 elements before that. And so he set aside himself to try to figure out a pattern, a way to write out all the elements so that all of their properties would repeat. And basically, this idea that every so often is if you rank the elements by their atomic mass, that you will basically see repeating characteristics of those elements. It's called the periodic law. And so he used this law and was able to basically create what he called a periodic table. And if you look over on your right, this actually is Mendeleev's periodic table in Russian, because he's Russian. It is oriented different than ours. If you sort of look right over here, you can sort of see there's hydrogen right there. It's sort of not at the top left. It's actually sort of, so this periodic table has been rotated 90 degrees and then flipped. So you can then sort of see we have, boron, carbon, nitrogen, oxygen, fluorine coming across there. It's sort of backwards from ours. But this is what he came up with. And it turned out that this periodic table did explain or did show the repeating characteristics of the elements, and but more specifically, it actually gave the ability to show a prediction. If you look carefully, you will see, and it may be difficult to see on your screen, but there are 2 elements that are right here, 68 and 70. If you notice, they have question marks in front of them. And the reason why is because in order to make this periodic table work, Mendeleev basically said, I've got some gaps. I've got some areas where we don't know any elements that would fit these characteristics, but the pattern says there should be elements here. And so he published this periodic table, and actually it turned out that once he had done that, is within a few years, is that one of these 2 elements was discovered, and later on the other one was. And so this showed that this periodic table had to be correct, because he correctly was able to predict elements with certain properties that hadn't even been discovered yet. And so this is Mendeleev's periodic table. The modern periodic table is somewhat different. Obviously, orientation makes it a little bit different right there. But overall, the main key about it is that while Mendeleev ranked his periodic table with respect to atomic mass, the periodic table that we use is ranked with respect to atomic number, that is the number of protons, because there are a few elements that don't quite match up if you do it by atomic mass. And so to look at the modern periodic table, let's take a look at what we've got here. This is once again an example of it. You've seen this before. Periodic table is categorized into periods and groups, and then also families. So periods is the reason why they call it the periodic table. A period is basically a set of elements that then will repeat a pattern of characteristics with another set of elements. And so effectively, in terms of what really is going on here, what a period is a period is basically the horizontal rows that you see on a periodic table. So you can sort of see we've got period over here, and so the first period would be going across here, hydrogen and helium. The second period would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on and so forth. The 5th period would be going across right here. And so that sort of tells you about periods. So periods are just numbered, so the first period, second period, third period, and so on and so forth. It simply just tells you that that means that lithium is going to have a similar characteristic to sodium, second and third period, then potassium, rubidium, cesium, francium. These are all have similar characteristics. And in the same way, beryllium, magnesium, calcium, strontium all have the same characteristics. They repeat as it goes from one period to the next. So periods are horizontal rows going across a periodic table. Next one here would be groups. If a period is the horizontal row, the group is going to be the vertical column. And so group 1 would be this setter right here. Groups always have similar properties. And so lithium, sodium, potassium, rubidium are all very similar. Beryllium, magnesium, calcium, strontium, period 2 are the same way. Same thing for, if I take 18, helium, neon, argon, that particular group. And so groups are your, excuse me, are your vertical columns. And so they are numbered 1 through 18. Sometimes you will see an alternate way of writing these out, in which basically that we have 1A, then we have 2A, and then the ones all in the middle here that are in the D block are all going to be B's. And then we have 3A right here, and going across all the way up until you get to 8A for this final one. That's the older system of writing out groups. You'll see periodic tables that have both of these on here. It's probably simpler to go ahead and just use the group numbers 1 through 18. That is the modern way of doing that, of writing those out. But just be aware that sometimes the groups are written in that sense. The next topic that we have here are families. Now, we said that within groups is that what we saw is that groups all have the same characteristics. And so we could go and we could take, say, these guys right here, these elements, and they have the same characteristics. And so in a lot of ways we can talk of them as being not just a group but as a family. Now, groups are sort of defined by what number they have. And so we said that, it's group number 1 is what that is. But a family will typically have another name. It'll have a name that actually describes what the elements are like. And so these are listed in the box that's sort of in the middle right up here, right up in there. So in this case right here, group 1, that particular family is called the alkali metals. And you can sort of see that that's what it's got listed right here for alkali metals right up there. And so the alkali metals are these ones that are in group 1. They are called alkali. The word alkali comes from a root in Greek, which basically means salt form, or means basic, like you said, of an acid or a base, because the alkali metals are typically involved in the creation of bases. And so those are the alkali metals. The next set that we have here are going to be sort of right next door to them, which are going to be in group 2. And those guys are the alkaline metals, or sometimes called the alkaline earth metals. So that's them right there, sort of the blue dot there. And so alkaline earth metals are those right there. The next ones that we will talk about here are going to be way over here. These are our red ones that are in group 17. Those guys are the halogens. The halogens, this is the one that comes from the Greek word halos, meaning salt. Gen is like the word genesis, to create. And so these would be salt creators or salt formers. The reason why is because most salts you run into have one of the halogens involved. And so those are your halogens right there. The next family we have here are these at the far end, right here, group 18. Those are the noble gases. The noble gases are called noble gases because they generally don't react with anything. They very rarely ever react and form compounds with other elements, and so they're considered to be noble because, like nobility, they don't deal with the commoners. They are off by themselves, and so they're called the noble gases because, well, as far as elements are concerned, they're pretty stuck up. So those are the noble gases in group 18. We have a couple other types of families that we have here. One is going to be that most all the things you see in the D block, right in the middle, and I will include a couple here that actually don't involve. Those are just the purple ones, the ones that really we're interested in here. These are called the transition metals. These transition metals, because of the fact that they do transition from the groups 1 and 2, from your alkalis and your alkaline earth metals, over to the rest of the periodic table over here on the right. And so those are the transition metals, and we'll talk about what metals are in just a second. So that's one set of ones we have here. The next ones are going to be the two green ones we saw before, and these two segments of elements that sit at the bottom. Now, as a whole, these are called the rare earth elements. For the most part, they are not very common. You don't find them on Earth very often. You've probably never run around and picked up a chunk of uranium that's sitting on the ground there, because these are not very common elements. In fact, some of them aren't really even like the ones that are up here, are almost entirely man-made, and you won't find them on Earth at all. So they are considered to be the rare earth elements. Those two rare earth elements, they come into two types. The first type are the ones that are at the top of the F block right here. These guys right here, those are the Lanthanides, as it says right there, named after lanthanum, the very first one. Technically that should be down below on the bottom section. And the next one down here are the Actinides, and so the Actinides named after actinium, which is their first element that starts them off. And so those are just some naming things of different families that we see on the periodic table. Next thing we'll talk about here are metals, nonmetals, and metalloids. So metals are first here. So what is a metal? Well, a metal is an element that basically shares its electrons fairly freely. Is that it gives them away to other elements, that they're able to move back and forth between elements fairly easily, and they form compounds with those. And what that means is, it means one, they conduct electricity very well because they can move their electrons back and forth. It means two, that they conduct heat very well. There are some other properties they have as well. Sometimes you'll hear about malleability or ductility, these abilities to flatten or stretch out into wire, but the main ones deal with basically their freedom of their electrons. Metals, for the most part, tend to sit on the left side of the periodic table. The dividing line between metals and nonmetals is sort of a stair-step line. You'll see it on certain periodic tables. It'll sort of look usually a little bit like this. I'll sort of draw it out like that. And so that's your stair-step line, and that really isn't very viewable at all. Let me see if I can get a better color on that. I'll use red. There we are. There's a stair-step line. So this is typically what is considered to be the dividing line between metals and nonmetals, with metals over here and nonmetals over here. And that can't be read at all. But you get the basic idea. So metals are over on the left side, nonmetals on the right side. And the dividing line roughly runs along that set of that stair-step line that I drew a little bit earlier. And so there is one exception to this, and that is hydrogen. Hydrogen sometimes acts like a nonmetal, sometimes acts like a metal. So it's sort of halfway between. It's on the metal side of the line, but it does have some characteristics like being a gas that make it closer to the nonmetal side. But sometimes it does give away its electrons pretty freely, so sometimes it acts like a metal. And in fact, if you cool it down to really, really low temperatures, then hydrogen acts very much like a metal. But you just fill up a balloon here, it really doesn't act much like a metal there. So it's sort of the halfway one right there. So metals on your left, nonmetals above the stair-step line to your right. There are a few elements that do show characteristics of both, and those are called the metalloids. And the metalloids are the ones that are in yellow right over here. And so they generally tend to follow that stair-step line. And so if you take a look when we drew that stair-step line out before, you could see that for the most part they're either just right above it or right below it. And so these are ones that have some characteristics of metals, some characteristics of nonmetals. Things like, say, silicon. That's one of the reasons why silicon is used in computer chips, because it sometimes acts like a metal, sometimes like a nonmetal. So sometimes it can conduct well, sometimes it can't. And so that lets you turn on electricity and turn on currents, which at certain times, which then basically allow it to basically work as a computer chip material. So these are your metalloids that sit right there. The root oid means like, but not exactly. Like I said, an android is basically a machine which is like a man. Andros is the word for man. And so a metalloid would be like that. If you made a robot that looked like a cat, it would be a pheloid, because feline is for cat, oid is like. So metalloids are elements that are like metals. Sometimes they are considered to be metals, like germanium and antimony and polonium. Sometimes they are not, like boron and silicon and arsenic and tellurium. And so those are your metals and your metalloids. And your nonmetals. Alright, so next topic is going to be on atomic radius. Now, atomic radius, you're basically describing how far out from the nucleus the outermost electrons generally are. Now, as we said before, because of the fact there's an electron cloud, is that the electrons are never actually at any particular point, but this is sort of an average. So on average, how big are certain atoms? And the below, you can sort of see we have something that's the shape of the periodic table. It has different sizes. These show you the different atomic radii for different elements. And if you take a look at this, one thing that you're going to notice is, well, there are two patterns here. The first pattern is going to be the pattern going from left to right. And if you notice on all of these, as it goes from left to right, then the atomic radius drops. And the question is, why does the atomic radius drop as you go from left to right? Well, if you think about it, is that as we go from left to right, we are adding electrons into the same energy level. So on our first one right up here this is the first energy level right up here for hydrogen, helium here. And so we add one electron into the first energy level. Now we add a second electron into the first energy level. Because we're adding the same energy level, we are originally sort of adding them. You can think of them at the same distance away from the nucleus. And so it's like we're sort of stacking them on a shelf. And so we've got sort of like a shelf right here, and we put the first one in here, and we put the second one in there, and then we're done. And so we're putting them at the same level, but the difference between hydrogen and between helium is that helium has 2 protons, while hydrogen only has 1. And if helium has 2 protons, that means it has twice as much positive charge that's pulling on those electrons, and so it's going to pull those electrons in much, much more tightly. It's going to have a much stronger pull on them. Since it pulls on them stronger, that's going to pull those electrons in, and so you end up with a smaller atomic radius. And so that's basically what's going on with that. So the same thing is going to be true once you go on to the next level, to the second energy level, is that lithium here, right there, has 3 electrons, but has 3 protons. When we get to beryllium, that's sort of next door to it, is that next electron that goes in that beryllium goes in the 2s orbital, and so it's at the same energy level. It would be put at the same distance, but beryllium has 1 more proton, and so that means basically it has another 1/3 more positive charge pulling on it, so it gets smaller. And the same thing, we're adding protons, adding protons, adding protons, adding protons, adding protons, adding protons, and so it shrink as more of those protons pull on those tighter and tighter. But then what happens when we go from neon, which is this guy right here, that's neon, to the one that's right after it, which is sodium. And so there's sodium right there, Na. Notice it gets a whole lot larger. Well, the reason why is because these electrons are in the second energy level, whereas the next electron that goes in, the second energy level is filled. It has to go in the third energy level. And since it's in the third energy level, it's going to be farther away from the nucleus. That's why the second fills before the third. The electrons want to get as close as possible to the protons. And so this says, the second part of this, which is that as you go down the periodic table, as you go basically down groups, then what happens to the element size? The element size gets larger, that the atomic radius increases, because of the fact that every time that you basically go down a step, that every time you go down an element in your group, is that what you're going to have is that it goes out to a higher energy level. So the first energy level might sort of be right up in here, the second energy level is out here, the third energy level out here, the fourth energy level out here, and so on and so forth. And so you keep increasing where you're putting your electrons farther and farther out as you add electrons, and so the elements get larger. So those are the 2 patterns that you see for atomic radius. Is that basically is that as you go from left to right, atoms will get smaller because you're adding electrons in the same energy level but increasing the number of protons. As you go down the periodic table, down a column or a group, that basically the elements are going to get larger because that while you are adding protons, you're also adding up to farther out energy levels. And so that's what's going to affect that. Next topic is going to be ionization energy. And to talk about that, we first need to talk about what that means. We said before that ionization, or an ion, is an element which has a charge. It's either lost or gained an electron. And in terms of ionization energy is specifically the amount of energy it takes to take away an electron. And so basically it is energy to take away, that should be T-A-K-E, away electron. So E minus for electron. So it is the energy to take away an electron. And so that's what ionization energy is. Now, if you think about it, this is very strongly related to atomic radius. Because if I have an element which has a lot of protons And so those protons put a whole lot of force pulling in on those electrons. It means they're holding really, really tightly to the electrons. And so those would be the smaller elements. And so the ones that have smaller atomic radii. And so ones like helium or ones like neon, they're very small. The fact that they're very small means they hold on to their electrons very tightly. So if they hold on tightly, how much energy does it take to steal an electron from them? A whole lot. And so on the counter side of that is that the elements that tend to be very large, that have very large atomic radii, those do that because the protons don't hold on to the outer electrons very strongly, and so it's very easy to steal one from them, and so those have a very low ionization energy. So if we were to draw out the pattern on this, what we would see is that going across along a period is that what happens is ionization energy is going to increase as we go across there. As we go down a group, then we can see they get larger. If they're larger, that means they're holding on to it less tightly, and so that means that ionization energy is going to drop. And so those are the two trends you see. So based on that, you could sort of take a look at this, what we've got right here, and you'd say that which atom has the highest ionization energy? It's hardest to steal an electron from. It would be the one that's smallest. And so looking at that, you'd say that's going to be helium right up here. And if you said which one is the easiest to steal an electron from, has the lowest ionization energy, that would be the one that's largest, which is this one right down there, which should be, I guess that's cesium in this case. Francium showed up. Francium would be even larger. It's got a little red X because francium really is radioactive and doesn't last long enough to really be able to measure it. But so the red X's are basically ones that are highly radioactive. So that's what we've got here. So in general, that's the trend that you see for ionization energy. Now, in terms of ionization as a whole, we need to take a little bit more of a look at the periodic table with actual elements rather than just atomic radii on it. Ionization, as we said, is whether you either take or give away an electron. Is that it basically because it's gaining a charge. And so actually I guess we don't have a periodic table here. Basically what we're going to see on this is that as you go across your periodic table, and I'm actually going to step back a little bit so that we can just take a look at this periodic table right here, is that elements that tend to be on this side of the periodic table, tend to be towards the left, are ones that, because of the fact that they say for group 1, things in group 1 only have one electron which is sitting in their highest energy level. They have a one valence electron. And so if they have this one electron sitting off by itself, because it's way off by itself, it's easy to steal. Because, well, as we said, is that, right over on that side is they're very large. It's easy to steal those electrons. Since it's easy to steal those electrons, that means that they're going to tend to give away electrons. If they give away electrons, then that means that they're going to generally end up with positive charges. So these tend to form positive ions over here on the left side. And the same thing is actually true all the way across here. So the dividing line is actually right about in here. So ones that are on that left side of the periodic table tend to, they don't always, but they tend to give away electrons. And the more left that you go, the more likely they are to give away their electrons and form positive ions. Now the flip side of that is the ones that are on the right side are going to tend to form negative ions. The reason why is because something like, say, fluorine has 7 valence electrons. It's very, very close to have, but those 7 valence electrons are all, if you take a look, are really, really close to the nucleus. So there, I mean, it's right in there. And so they're really close to the nucleus. And so any other electron that's around here, it says, ooh, I can get really close to these protons, which it's attracted to. And so it's going to join up to that side, and it's going to gain electrons. And so what you'll end up getting is you'll end up with the guys that are over on this side, for the most part, are going to want to gain electrons because that the electrons can get really close to the nucleus, and so they tend to be negative ions. And so this is basically the pattern that we have here. We will get to figuring out numbers on the next lesson, but for right now, all we can say is this, is that ones that tend to form to the left tend to be larger. They have larger ions, or larger elements, sorry. As larger elements, they tend to have lower ionization energies, and so it's easy to steal one, so they tend to lose electrons and become positive. Ones that are on the right side hold on to the electrons really tightly, and because of that, they bring them really close in, and so any other electron that comes near it will see their nucleus, and will see all those positives there, and is likely to be drawn in and captured, and so it will develop a negative charge.